Welcome to Rosny College Electronics series of videos. In the previous video we looked at how a NAND gate was made using 4 MOSFET transistors. The NAND gate had the truth table that looked like this. So there was the truth table from our previous video, where the output is low when both inputs are high, otherwise the output is high. And we call that a NAND, and we're giving a NAND gate this symbol. So it looks like a giant D with 2 inputs and a round circle on the output. That indicates that it's negated or inverse AND. And let's label our inputs A, B and Q. Okay, and I'll redraw the truth table. A, B, Q, 0, 0, 0, 1, 1, 0, 1, 1. And they were all true except for that one. Now we're going to look at how we can use these to create other gates. Now, a very important gate to create from this is what we call the inverter. So the inverter only has one input, and it changes it. So if the input is 0, it makes it a 1. If the input is a 1, it makes it a 0. Okay, so that's where there's a hint as to where its name, its operation in its name. That is, it's a NOT gate. So a NOT gate means that whatever the input is, the output is not that. If you look at how a NOT gate would work, so a NOT, the truth table for it, we've got only one input and one output. So if the input is 0, the output must be not that, which is 1. And if the output is 1, if the input is 1, the output must be not 1, which is 0. If you have a look at the truth table for the NAND gate, if both inputs are the same, so if both inputs are 0, the output is 1, and if both inputs are 1, the output is 0. So we could make a NOT gate by connecting both of these two inputs together, which eliminates these two. Because the inputs here are different, this is not a valid state for if they're connected together. So we can make a NOT gate by tying the inputs together and of a NAND gate, which has the effect of being an inverter. This is a very important circuit because it becomes the basis for many of our other gates. Let's have a look at a very simple one. We want to make an AND gate. Now we can't make an AND gate using just the 4 MOSFETs from before. So before we had our 4 MOSFETs arranged in such a way that both A and B had to be high in order for T3 and T4 to conduct, and T1 and T2 to not conduct, which connects the output to 0, which makes the output low. So that's the basis of our NAND gate. Now our AND gate is the inverse of that. So if we were to take the output of a NAND gate and make that the input of a NOT gate, it has the inverse effect. So let's have a look. If I were to have my 2 inputs A and B, I'm going to have some intermediate variable I'm going to call C. And C here is going to be identical to this up here, because it's just all I've drawn is a NAND gate. So the truth table for C will look identical to this. If I then connect that to both inputs of another NAND gate, then that part is identical to my NOT gate. There's only one input now, or one intermediate variable, which when both connected to both inputs of this NAND gate become inverted. So if C is a 1, then Q, which is our output here, is a 0. Likewise, if C is a 0, Q will be a 1. So let's draw the truth table, and we're going to include the intermediate variable for the moment, just so I can demonstrate. So again, we've only got our 4 possible input states. Now C, it's as if I don't have that there, I'm just looking at C here now. C is identical to our NAND gate up here, so the output is going to be identical to this. So 1, 1, 1, 0. Okay, I don't think I need to rehash that. Likewise, C now is the same as our input to this gate up here. So if A was 0, then Q is 1. So in this case, if C is 0, then Q will be 1. So we've got a 1, 0 at the bottom. And likewise, if C is 1, Q will be 0. So if C is 1, Q will be 0. And so our output of this gate is the inverted of our NAND gate, which is an AND gate. So we're back to where we were in the previous video, where I looked at an AND gate and I said both A and B are true. It gives the output is true. So if you have a look, this truth table, A and B has the same pattern as before, and Q is 0, 0, 0, 1, and we've got that in our truth table here. I'll leave it up to you as an exercise to look up the different different gate arrangements for the different gates. I'll write down what the gates are. So we've got 7 different types of gates. So the 7 types of gates are, and we've seen 3 already. So we've seen an AND and a NAND. So we've seen an AND and an AND. We've seen a NOT. And the other gates are, there's an OR, and there's an inverted OR, which is a NOR. And there is a XOR, exclusive OR, and there's an inverted XOR, which is exclusive NOR. Now the general operation of these, the AND, if both inputs are high, the output is high, otherwise the output is low. And this is the inverted of that. So you say if both inputs are high, the output is low, otherwise the output is high. The NOT gate, it just changes the output from the input. So if the input is 1, the output is not 1, so it's going to be 0. Likewise. The OR gate, if the input is if both inputs are 0, the output is 0. But if one or both of the inputs is 1, then the output is high, or 1. The NOR is the inverted OR gate, so if both inputs are 0, the output is 1. Otherwise, the output is 0. The XOR works a little bit differently. Exclusive OR is what the X stands for, is where if only one of the inputs is high, then the output is high. Or another way to think of it is if the inputs are different, the output is high. The XNOR, sometimes called a equivalent, is where it's the inverted XOR. So if the inputs are different, the output is low, or the output is high when the inputs are the same. So if A and B are the same or equivalent, then the output is high.